Well, hello dear students, how are you all? Hope you are doing great. Okay, so today we will conclude chapter 3, that is current electricity, by learning Wheatstone Bridge, or few people call it Wheatstone Bridge, it's fine. So Wheatstone Bridge, where you will find out the unknown resistance in terms of the other known resistances, and a modified, or you can say advanced version of Wheatstone Bridge, that is meter bridge, or also known as the slide wire bridge. Then we'll talk about the potentiometer, which is an ideal voltmeter, or you can say better version of voltmeter, and how does it help us to compare the EMF of the two cells, two standard cells, which may be Leclanche cell or Daniell cells. Okay, and it also helps us to determine the unknown resistance of the cell, sorry, internal resistance of the cell. Okay, so these are the two applications of the potentiometer. So that let's take this one by one thing at a time. Be patient, listen to each and everything carefully, sit with notes and pens, so wherever you have any doubt, write it down and you can ask it. Okay, so let's start then. Be focused. Okay, what is Wheatstone Bridge? So Wheatstone Bridge, an arrangement of four resistances, out of which one is unknown. So we determine the value of this unknown resistance in terms of the other three resistances. Okay, so we will here use the Kirchhoff's rule in finding out this unknown resistance. And to find this, what will we do? We will follow the null deflection method. That means, let's say for example here we have resistance P which is not known. Okay, so this is the unknown resistance. We want to find out the resistance P. Then what shall we do? We will adjust the resistance here in such a way, for example here this Q, we will adjust this value of resistance such a way that no current passes through the galvanometer. The galvanometer should show zero deflection, so that is why this is called null deflection method. So what shall we do then? Let's apply this Kirchhoff's rule to find out this resistances. Okay, so first let's apply the Kirchhoff's rule on the loop ABDA. So here is A, so that's your B, D and A. So in this loop we are going anti-clockwise. You must revise Kirchhoff's rules before doing this. Okay, so first let's say we are going in this arm. So in this arm, what is the product of current and resistance? It is I1P. Then here along this arm it will be current is Ig, resistance is G. Capital G here is the resistance of the galvanometer. Okay, now when you go from in the arm D to A, the current is coming towards you. You are going anti clockwise, but I to R is anti-clockwise, so it will have to suffer, and it comes with a negative sign. So I to R here has a negative sign. Is that clear? So you have applied the Kirchhoff's rule in this loop ABDA. Okay, now similarly we will apply the rule in BC here, this side BCDB. So we will apply the same Kirchhoff's rule here in this loop. Again we are going anti-clockwise, sorry, clockwise. Okay, so let's go from B to C. So in this arm, what is the product of current and resistance? It is I3Q, it is there. Okay, now if you come from C to D, then I4S is coming towards you. You are going this side, you are going clockwise, and this here is anti-clockwise, so it will also have to come with the negative sign. So I4S is here with the negative sign. Now if you go from D to B, then this in this arm also IgG is coming towards you. So whatever is coming towards you, that should come with a negative sign, because you were going clockwise but these terms are anti-clockwise, so even IgG here come with a negative sign. So here we have two very important equations. Okay, so now let's say that you somehow chose the value of resistance here in such a way, because see, we want to here find out P, so we here choose the value of certain other resistances. For example, here this Q resistance, if I choose such a value that no current passes through the galvanometer, so this Ig, that is the galvanometer current, the current which is required to produce the deflection or maximum deflection inside the galvanometer, is zero. So if this current is zero, then you can say the bridge is balanced, and this is something which we will keep on doing in next few experiment as well. You have 2-3 experiment in 12th standard where you will follow this thing. You will bring down zero deflection inside the galvanometer. Okay, so when you have balanced the bridge, no current is passing through the galvanometer. If Ig is 0, then what will happen? Let's say I1 was the current here in this arm, the same current will flow through this arm as well. So I1 and I3 will become equal. Similarly, this I2 and I4 will also become equal. Why? Because there won't be this arm BD then. This arm BD with the galvanometer in between, that arm, as if it's not there, it disappears. Okay, disappears means just into calculation. Physically it will be there. Don't be the magician and try to make it disappear inside the laboratory as well. Okay, so if you substitute this Ig is equal to 0 in this equation 1 and 2, then this will become I1P is equal to I2R, and this second equation, what will it become? This is, sorry, this is the second equation. It becomes I3Q is equal to I4S. Okay, but we have seen here that I1 is equal to I3. So if you take the ratio here, this I1 gets cancelled, I1 becomes I3, it gets cancelled. So what we have ultimately is P by Q, and here we will have R by S. Okay, so when you divide equation 1 by 2, you have ended up with this equation, and that equation here is available or derived only when the bridge is balanced, and because this term have disappeared all the terms of galvanometer here. So there is no current passing through the galvanometer when the bridge is balanced. Okay, this Wheatstone Bridge, it's a Wheatstone, which was discovered by a British physicist in around 1843. So Wheatstone Bridge is sensitive. It is very sensitive if it shows very large deflection, even for a small changes of resistances inside the circuit. When you change even a bit of the resistance, the current increases abruptly and it shows large deflection. Okay, and the next is K. When will it be most sensitive then? In what scenario the Wheatstone Bridge must be very sensitive? So it is very sensitive, then all these resistances PQRS are almost of same magnitude. Okay. Okay. So when you have balanced this Wheatstone Bridge, the potential difference between B and D, where the galvanometer is connected, is 0. That means the potential difference between terminal B and D will become 0 because no current is flowing through the galvanometer. And what is this advantage of Wheatstone Bridge method? Why are we using it? What is the advantage it is offering over this voltmeter or any other devices? Okay, so it is a null method. It is a null method, so the internal resistance of the cell or even the resistance of the galvanometer here, it does not affect the null point method, right? So it doesn't affect it. Let's talk about the meter bridge now, which is also known as a slide wire bridge, because we slide a jockey over the wire, which may be mostly an alloy like constantine or manganese, right, to get the zero deflection inside the galvanometer. That's why it is also known as the slide wire bridge, and it works on the principle of the balanced Wheatstone bridge. Here we want to find out the unknown resistance X. This is the diagram of the Wheatstone bridge. Meter bridge. Okay, meter bridge is, you can say, a modified Wheatstone bridge, a more complicated structure. So here is a metal strip, there is one more here, and that is third one. So these metal strips here are connected to A and C in such a way that it completes the circuit. This is a 100 centimeter long wire between A and C, which may be an alloy. Mostly it is an alloy. There is one gap between these two metal strips where we connect a resistance box inside this circuit. Now here there is another gap where we connect a box resistance or any kind of resistance your school provide you, that resistance S, which is unknown, we connect it there, right? Now here in this central metal strip, it is connected to the galvanometer. So here it is connected to galvanometer, and the other end of the galvanometer is connected to jockey. Now when you will introduce certain resistance here, and for that certain resistance get a deflection on this wire, 100 centimeter long wire. Let's say you get the zero deflection at point B, then this AB will give you the third resistance. Well, you have seen in the Wheatstone Bridge that it was P by Q is equal to R by S, right? So R and S are given to you here. This R comes from the resistance box, S you want to find out, so you don't have P, you don't have Q. So P and Q here will be in terms of the length of the wire. You know the resistance formula. What is the formula? R here is equal to, it was rho L by A. Now area of the wire is constant. Resistivity, the material's characteristic, that is also constant. So resistance is directly proportional to length. See, so since the bridge wire is of uniform cross sectional, resistance is directly proportional to length of the wire. Let's say that you get a balancing length at B, then this AB is your first balancing length and you call it L. So what is AB? That is your P, that is the resistance of wire AB, and the balancing length here what you have got is sigma, sorry, L, right? And what is the length remaining now? So if you have got here L, then the remaining length will be 100 minus L, and that is known as BC, and BC we say that it is equivalent to resistance Q, right? So what is sigma? We have introduced sigma here also. Sigma is the resistance per unit length. What is sigma? Sigma is equal to small r, resistance per unit length. Now sigma is constant, so you can take this L on other side. So R here is equal to L into sigma. As length increases, resistance will also increase. Is that clear? So this resistance, when you say it's for AB, small r for AB part, when you take the length L. Now if you write the small r for that another length AB, that means for BC, so that is a small r for what length? It is 100 minus L, okay, and that is equal to, what will it become? That is, here I have mentioned 100 minus L into sigma, right? So get a balancing length here on this on this wire by sliding a jockey, and call that balancing length one arm certain resistance P and another arm as resistance Q. Okay, the sigma here is constant, so put sigma L, and another is sigma 100 minus L. Sigma gets cancelled, so this here is your P by Q. That's it. So R by S is equal to P by Q. Instead of P by Q, substitute this value L divided by 100 minus L, and as we wanted to know what our value of S is, make S the subject, and you have ended up with this equation R into 100 minus L by L, where L is clearly visible from the balancing length, whatever it is, right? And R is the resistance that you have taken out from the resistance box. So if you know L, R and S, you can easily, L and R, you can easily find out the unknown resistance S. Okay, now In this experiment, they may tell you to find out resistivity also. So what will we do? With the help of the screw gauge, we also call it a micrometer screw, you try to find out the radius of this wire, right? Because you know resistivity rho is equal to RA by L. You know what is the formula? यहाँ पे मैंने लिखा था ना, देखो R is equal to rho L by A. If I make rho the subject, equation become RA by L. So then you would say कि sir here you have not written R, I have written S. S is the resistance which you have derived here. So if you have derived this resistance, put it here, simple. So S into area divided by L dash. Okay, L dash is the length of your wire. Then this area is pi r square, where r is the radius of this alloy or the radius of the wire you have been using into this meter bridge or slide wire bridge, right? So you have to measure it, find out it, and you can find out the resistivity also. So this is how this meter bridge or slide wire bridge helps you find the unknown resistance with the balancing of the Wheatstone bridge or the balancing of the meter bridge, and when it is balanced, there is zero deflection inside the galvanometer. Okay, let's now talk about potentiometer. What is potentiometer? What is it used for? Potentiometer is an instrument which measures the unknown EMF of the cell without drawing any current from it. Wow, that is something different. Yes, because it is different from voltmeter. Potentiometer, you can say, is a substitute of the voltmeter, and in fact it is an ideal voltmeter. It is a better voltmeter. Voltmeter, you know, you have learnt it in 10th standard that voltmeter is always connected in parallel, and ideal voltmeter should have infinite resistance, but voltmeter doesn't offer that very high, you can say, the resistance. But yeah, you can have that higher value of resistance with the help of this potentiometer. So that's why this potentiometer has slight upper hand over the voltmeter when it comes to resistance. Yes, it definitely has. And it on the like instead of voltmeter, it doesn't draw any current from cell. If you talk about voltmeter, when you connect it to the cell, it uses its voltage or its EMF to show the deflection. So that's the bad part about voltmeter. Well, not able to get it, let's study it further, then you will understand everything about this potentiometer and voltmeter, which is better, why is better. Okay, so first you need to understand what is the principle, how does it work, and what is the construction of the potentiometer. Okay, the principle it works on is simply derived from the Ohm's law. You know Ohm's law, V is equal to IR. If you substitute R, it becomes rho L by A. So here I have substituted the value of R, and that value here is rho L by A. So from this, we can now state the principle. Okay, when a constant current I, what is it? When a constant current I flows through a wire of uniform cross-sectional area and composition. Composition, that means its resistivity is also constant. So when a constant current I flows through a wire of uniform cross-sectional area A and composition rho, then the potential difference V across any portion of the wire is directly proportional to this length. Only L was left there. Okay, so potential difference was directly proportional to length. I have used the word for any portion. That portion is measured from A. The length is measured from A. Whatever may be the length, accordingly there will be the potential. So we have kept current constant, rho constant, A constant. So we have three parameters constant here. So because instead of this three constant, we put a single letter K, and that equation has become V is equal to KL, where this K is equal to I rho by A, and is also known as the potential gradient. I have told you earlier in the second chapter when we learnt E is equal to minus dV by dr, that when something changes with the distance or related to the distance, then you use the word gradient. So here potential is changing with the length, so we have used the word potential gradient. So K is equal to V by L, or you can simply say it is the potential drop for the given length. Okay, the unit of K is equal to volt per meter. That's the SI unit, but in practicals we mostly use is volt per centimeter inverse. So that is the principle of the potentiometer. The principle of potentiometer, that potential drop is directly proportional to length, right? Because we are not changing current inside this circuit, the current is provided by this external battery. You will not keep on changing the wire in between the experiment, so rho is constant. You are not increasing or decreasing area is also constant. So the only thing that was left was the length. So potential is directly proportional to length, right? So let's go for the construction now. So what is the construction? You can see it's a 4 to 10 meter long wire. Generally we connect it between 2 points A and B here. Here we have taken 4 meter long wire. So this will be 1 meter wire. Then there will be this metal strip which will provide the closed and continuous path for the current. There will be some screw or some arrangement. You will tight the wire there. Then current will flow from here to here. Then that will be the direction of the current. It was coming from this side. Now here the current again will flow this way and this side. So this is how the whole current will keep on flowing inside this circuit with the help of this battery we have connected externally. And this battery here is called auxiliary or driving battery or driving circuit. This part here of the circuit is, what do we call it? That is auxiliary or driving circuit. Okay, the wire we use here will obviously have uniform surface area as well as its composition, so that will remain constant. You will not change it, and they have very high resistivity and low temperature coefficient of resistance. That means the resistivity or resistance doesn't change throughout this experiment, because it's an alloy. Generally we may take constantine or manganese. Is that clear? So constant current is flowing through this circuit, and therefore potential gradually falls from A to B. Well, how does potential falls from A to B? As you go from A to B, how is it decreasing as the constant current is flowing through it? Try to find it out, and you can write the answer in the comment box there. Okay, we are here studying two applications of potentiometer. Let's learn the first one, where we are comparing the EMF of the two primary cells. We here will use Leclanche cell and Daniell cell that are made in your laboratory. Okay, so let's say E1 and E2, or you can say epsilon 1 and epsilon 2 are the EMF of the two cells which are to be compared. They are connected to this point A. To point A, we have connected this auxiliary battery as well with the epsilon EMF, with the EMF equal to epsilon. To this point A, this A1 and E2 are also connected, right? So what will we do? We will get the balancing length for both of these battery by putting this plug in this A here and in B turn by turn. So first we put the plug in A, then we put the plug in B. We will bring both of this cell one by one into the circuit, get their balancing length, obey the potentiometer principle, and that's it. Your EMFs are easily compared. Wow, is it so simple? Yes, let's go for it. So you have to learn how to write the diagram. So you have to mention the diagram, which I have not write everything in this page. So you will have to learn that, right? So you can write down that the two cells whose EMF are to be measured are connected to A. Also the external battery is connected to the positive terminal here. Remember, you need to take care of this terminal. The positive of both the cells whose EMF to be measured is connected to A, and also the positive of this external battery here. Okay, and this battery, the EMF E must be greater than this both of it. both of the cells which are connected here, otherwise your experiment will create a lot of problem. You will never be able to get the answers. So this external battery, when you do this experiment, you need to be very careful with this, because students do a lot of errors while performing this, and it is very challenging experiment. Okay, well, so let's do the experiment. Write down all about diagram. So you have inserted this key here between A and C. So when you insert the key between A and C, what will happen? You get the balancing length J1, that is for this cell epsilon 1, and you call that AJ1, let's say length L1, right? So AJ1 is what? There is the balancing length. So balancing length, that means the galvanometer here will show zero deflection. There is no current passing through galvanometer. Then at that null point, when you get the null point, you can say that E1 is equal to KL1. That is the potentiometer principle, that the EMF or the voltage is directly proportional to the length, because there is constant current flowing through the wire of constant area, right? So everything is constant, so the balancing length give you the EMF here of the first cell. So E1 is equal to KL1, or you can say epsilon 1 is equal to KL1. So you have got it for the first cell. Now what will we do? We will introduce we'll put the key or plug in this CB. So when you put it between B and C and get the balancing length, call it length 2. AJ2 is the balancing length for the second cell epsilon 2. Then again, from the principle of potentiometer, you can write down that this E2 is equal to KL2, right? E2 is equal to KL2. Now you have got two equations. Take the ratio, so epsilon 2 divided by epsilon 1, or E2 by E1, that will give you L2 by L1. Now L2 and L1 you already have got as a balancing length here. So those are the known value. The only thing you want to find out here is epsilon 2, because this value is also known. One of them definitely is a standard cell of known EMF, so that is our epsilon 1 here. You take it on the other side and you can find out the EMF of this second cell there. Is that clear? Good. And as I have told you earlier, that this EMF of the auxiliary uh, battery or cell that we are connected externally here, it must be greater than both of them. Is that clear? So this is how we will use potentiometer to get or to compare the EMF of the two primary cells, and it is very easy. Just introduce one cell at a time, get a balancing length, get this apply this potentiometer principle carefully. You will get these two equation, E1 KL1, E2 KL2. Just take the ratio and that's it. Your comparison of two primary cells is done. Is that clear? Then you might say, how is it comparison? Because you have got this ratio, E2 by E1 is equal to L2 by L1. Got it? Now let's go for the second application of the potentiometer, where what shall we do? In second application, we are measuring the internal resistance R of a primary cell by a potentiometer method, right? Or potentiometer. So what is small r? That is the internal resistance. If you remember, I have told you to remember this equation. R is equal to epsilon by V minus 1. Okay, epsilon by V minus 1 into R. That is the value or equation of the unknown resistance. Okay, how shall we do it then? Well, let's go for it. So you can see the potentiometer, the A is connected to the positive terminal here, and this is the cell whose internal resistance we want to measure, and that is the positive of that cell is also connected to A, right? And the positive of this battery is also connected to A. Now, if this cell has higher EMF than this battery, then it will start giving current. But as I have told you earlier, that That is not the scenario. That is never going to happen, because we here are keeping the external voltage or this auxiliary battery EMF always greater than this. So current will be flowing in this direction, right? Current will be flowing with the help of this battery. Got it? Good. So what shall we do? We first put the K1 here. We will close this key and we'll keep K2 open. If you keep K2 open, then what you are measuring here is EMF, because I have told you EMF is measured in open circuit condition. When the circuit is open, what you measure is EMF, not the potential difference. When you don't put this K2, you are not bringing this epsilon here. You can say the potential difference. You are not bringing the potential difference into the picture, because when K2 is open, what you measure is EMF, and epsilon here is the EMF of the cell, right? So you move the jockey, get the balancing length, and let's say L1 is the balancing length for this K2 open. So what you have measured here is the EMF. Remember, it's not the potential difference. Okay, then from the principle of the potentiometer, that EMF is equal to K L1. L1 is your balancing length, K is your potential gradient, and galvanometer at this point will show zero deflection. Okay, now let us introduce certain resistance from the resistance box, and when you introduce it, it's of no use if you don't put this K2 here, right? So when K2 is inserted, key K2 is inserted, introduce certain resistance. Now get the balancing length, call it L2, but now the circuit is closed. So what you are measuring here is not the EMF. Here we did it EMF. Now what we are measuring here is the potential difference, because it's a closed circuit. The current is flowing inside the whole circuit. It's a closed one. We have learned it earlier that what is the difference between the EMF and the potential difference. EMF is measured when the circuit is open, and when the circuit is closed, then what you measure is not the EMF, that is the potential difference, right? So balancing length is L2. So write down that this equation V is equal to KL2 from the principle that potential is directly proportional to length, right? Okay, now we know that the cell we have used has internal resistance R. I is the current flowing inside this circuit, and we have shunted this cell EMF with the help of the resistance box. Shunt means to connect a resistance parallel to something. So here we have connected a resistance parallel to the source of the EMF. So this is called shunting of this cell. Okay, so what according to Ohm's law will it become here? We know that E, that is the EMF, is equal to, there are two resistances, a resistance from the resistance box, and this is internal resistance. So E is equal to I into R plus R. Okay, if you take I common, it becomes R plus R. If you want to find out current, you can use this equation. If you don't write it, then also it is fine. But yeah, it is just for the numerical purposes. Okay, we have got these two equation. Here is equation 1, that's your equation 2. Just to find out the internal resistance, take the ratio of 1 by 2. Then what we have here is E by V, that is L1 by L2. Now put this value in this equation, E by V here. Okay, we know that internal resistance R is equal to E by V minus 1 into capital R. So instead of this E by V, put L1 by L2, where L1 and L2 are known value. You have discovered this value from the balancing or by bringing the zero deflection inside the galvanometer. So this is your ultimately equation to find out the internal resistance R. Is that clear? Okay, so see, with the help of the potentiometer, we have measured or we have discovered the EMF of the cell. We have also measured the potential difference V by putting this K2 key in the circuit or by bringing cell into the picture. Okay, so this is the use of the potentiometer, that it measures the potential difference, it measures the EMF, without drawing any current from it. So here didn't it draw any current from this cell whose EMF is to be measured? No, because the EMF of this is obviously less than this battery. So we are not drawing anything from this. We are drawing everything from this powerhouse, this cell, this battery. Is that clear? And it is a null method device. This potentiometer is a null method device. Okay, so what happens at null point when the galvanometer is 0? It is not drawing any current from the cell, and this question was asked in this last 2020 board examination, and it was very tricky answer. It had two or three correct option. Okay, so potentiometer is preferred over voltmeter, or you can say potentiometer is an ideal voltmeter. It works on the null method device and it draws no current from the cell whose EMF is to be measured, contrary to voltmeter. Voltmeter will draw at least some current to show the deflection in itself. Is that clear? That is why potentiometer is preferred over the voltmeter. Got it? Good. So these are the two applications of the potentiometer. That's it. So a very big thank you to all of you for watching and listening to me. Now keep reading, keep revising. Thank you. All the best.